All right. Well, after yesterday's review, I am very excited to be moving on to some brand new stuff today. We're going to talk about Hess's law of heat summation. And I've got our learning objectives written on this very first slide. By the end of today's lesson, you should be able to say, I can explain Hess's law of heat summation, and I can manipulate reaction equations to calculate an unknown enthalpy change. And before we start talking about Hess's law itself, I want you to keep in mind something that Mr. Belter brought up at the very beginning of this thermochemistry topic, and that was the conservation of energy. He said that this is something that we often associate more with physics, which is true. It is an important part of physics. However, it is definitely an important part of chemistry. And Hess's law is going to demonstrate to us exactly how energy is conserved, even over multiple steps of reactions, which is exactly what we're going to talk about with Hess's law. So, before we dive into the meatiness of the law itself, I'm going to share a little bit of information about Hess, because I love a good bit of science history. So, Hess was a Swiss-born Russian medical doctor and chemist who was really interested in the theoretical side of chemistry. So he was born in 1802 and died at a very young 48 in 1850. But this time for chemistry was a booming time, really. Lots of new elements were being discovered and their properties were being researched. But like I said, Hess was very interested in the theoretical side. So while he was, of course, interested and fascinated by all these new developments, he was very interested in how different molecules interacted and what that meant for chemistry as a whole. So he was actually doing research on hydrates of sulfuric acid and realized that he could start with different intermediates, so different products that would eventually get him to the same final product, and they would always release the same amount of heat, which is exactly what Hess's law is. So, Hess's law states that the enthalpy change of an overall process is the sum of the enthalpy changes of its individual steps. Again, a while back, we talked about state functions, and state functions don't depend on the process. They depend only on the beginning and the end. And Hess's law is kind of just a fancy way of restating that. It doesn't matter how many steps we take to get to our end, but from where we start to where we end up, that overall change in energy, that overall, whether it absorbs energy or it gives off energy as heat, or in some cases as volume or pressure changes, that is what matters, is the beginning and the end. We can have lots of intermediates. We might have some intermediates that require energy, some intermediates that give off a lot of energy, that release a lot of energy, very exothermic. But the part that we really need to focus on is the beginning and the end. And why is it important for us to know how to do this, to know how to use Hess's law? Well, there are different reactions that we cannot do in a chemistry lab. Some are maybe perhaps part of larger biological processes, so it's very hard to isolate, or nearly impossible to isolate, the individual reactions. And knowing how to calculate enthalpy changes allows us to study some part of them at least, and to understand how that energy released affects the system that it's a part of. Some reactions might just simply take too long. Some might go too quickly. Some might require too much energy or release too much energy for us to just physically do in a lab. So knowing Hess's law allows us to understand and to still study and work with all sorts of substances and chemicals. So how do we use Hess's law? Well, Hess's law is a little bit of math, and we're going to use math for both numbers and for equations. So we're going to have to use our algebraic brains and think of chemical equations almost like they are numbers. We're going to do some cancellations, and we're going to do things that look a lot like things we would do in a math class, but with different substances and different chemicals. We're going to start off with a pretty simple example, and then we'll do a much more or slightly more complex one so you get a feel for what this looks like both in a basic sense and how it looks when you go a little bit more complex. But before we do the actual calculations, we're going to look at kind of the basic format of how you do the calculations, how you use this information to find the numbers that you're looking for. So when you're using Hess's law, you're trying to find an unknown enthalpy. So you've got several sets of reactions. Usually it's going to be 2, 3, or 4. Could be more, can't have less than 2. But you're going to have one that you do not, sorry, not 2. You're going to have at least 3. You're going to have 3, 4, you could have more. But you're going to have one whose enthalpy change you do not know. So the first step is identifying your target equation. Look at the ones that you have, figure out which one you don't have an enthalpy change for. And as you're looking at that, it's probably good to note the number of moles of each reactant and product, because we already know that enthalpy is directly related and proportional to the molar ratios, molar quantities. So it's important to note numbers of moles of reactants and products. Next, we're going to manipulate our equations so that our target moles of products and reactants are on the correct sides of the equations. This is what, when I was talking about earlier about how we're going to use our math brains, we're going to use some algebra with our equations. This is where this is going to come into play. Basically, we need to make sure that when we cancel out all of the unnecessary molecules, so we're looking at a target equation, which means that we're going to use the other equations for who we have changes in enthalpy. We're going to have to cancel out all of those unnecessary molecules, all those unnecessary substances. We have to make sure that they're on the correct sides of the reaction arrow. We might have to reverse reactions, which means that we'll have to flip the sign of our change in enthalpy, because if we're reversing a reaction, it means that we're changing the whole direction and it's completely changing whether or not something is exothermic or endothermic. We might also have to multiply by different coefficients so we get the appropriate molar ratios, which is another thing that we're going to have to keep track of. Because again, if we multiply an equation by a coefficient, we also have to multiply that enthalpy change by the same coefficient. And our third step in using Hess's law to calculate an unknown enthalpy is just simply to add the equations and the enthalpy values to find our unknown. Once we've reversed our signs appropriately and multiplied by the appropriate coefficients, this is really simple. And we'll see just how simple it is in our very first example. So, our first example is going to be the formation of nitrogen dioxide. This is a reaction that actually naturally occurs when there is lightning. Diatomic nitrogen reacts with diatomic oxygen in the atmosphere to form nitrogen monoxide. And then because there's an excess of oxygen in the air, that nitrogen oxide will react with diatomic oxygen to form nitrogen dioxide. So when we look at these three different equations, we can see pretty instantly which one it is that we're looking for that doesn't have a known enthalpy, and that's the one that we're looking for. Sorry about that. All right, and it's of course this third one. So when our nitrogen gas reacts with oxygen gas to form nitrogen dioxide gas. That is our target equation. So what we're looking for is to make this reaction and this reaction add up to this reaction. A good starting place, so we've already completed our first step, which is to identify our target equation. Now we're going to manipulate the remaining equations so that they will add up appropriately. A good first step is to look at all of the elements, the chemicals in this, our target equation, and find one of the other two equations that contains one of these molecules and is only found in that equation. So we're looking for one of the other two equations that is the only equation that contains one of these three chemicals. So if we look up at our first one, well, here we've already got our diatomic nitrogen. So that might be a good starting place. Let's check our second equation. Nope, we've got nitrogen monoxide, we've got oxygen. So we're going to start with this first equation. And what we want to do is make sure that if we were to, add a little plus sign right here, if we were to add a little plus sign and we were going to start adding these all together, would we have the appropriate values down here? Will all of these add up to this? So we are looking for 1 mole of diatomic nitrogen. We've got that, so we don't need to mess with the nitrogen. We've got 1 mole of oxygen. Well, we've got 2 moles down here. But if I look at my second equation really quick, I've already got a second oxygen. So we're going to be safe on the oxygen. I don't need to mess with the coefficients. And our nitrogen is on the appropriate side. So earlier when I was talking about the sides of the reaction arrow, if I have a reactant that is the same as a product, because they are on opposite sides of our reaction arrow, they will cancel each other out when I'm adding them together. Which is why when we add straight down, which is why our nitrogen is in the right spot. We know that our nitrogen is in the appropriate place. It's on the correct side of the reaction arrow. As of right now, it doesn't look like we need to manipulate our first equation at all, which means that we don't need to do anything to that enthalpy value either. Let's take a look at our second equation. We've got nitrogen monoxide right here. Well, if I look back up at my first equation, I've got 2 moles nitrogen monoxide on the product side. So when I add these together, this is going to cancel this out and will be balanced. We've got our second oxygen molecule, and then we've got 2 moles of nitrogen dioxide. Perfect. That means that I don't need to manipulate my second equation at all, and I don't need to do anything to my enthalpy value either. When I add these up, to remind myself of what I'm canceling out, I'm going to draw an X through these, draw a line through these two, so that I have my single diatomic nitrogen, my 2 diatomic oxygens, and my 2 nitrogen dioxides. That means that I can also add up my enthalpy changes. And 180 plus minus 112 is going to be, oh good, sorry. That was too many steps, I apologize. There we go, 28 kilojoules. So, hopefully that seemed very simple. We didn't have to flip any signs, we didn't have to multiply by any coefficients. Our second example is not going to be quite so simple, but I think it'll be just fine. You'll get it right away. So here we're looking at dinitride pentoxide, the formation of dinitride pentoxide. And again, our first step is to identify our target equation. If we look, there's only one that doesn't have a known enthalpy change, so that means that this is going to be our target equation. Again, our second step is to start manipulating our other equations, and a good place to start is by looking for an equation that contains one of these chemicals and is the only one that contains it. So if we look at our first equation, we can see that we've got hydrogen, we've got oxygen, and we've got water. There is, in fact, oxygen in our target equation. However, I can see that there's also oxygen down here in our third equation, so I'm not going to choose to start with the first equation. If we take a peek at our second equation, however, I've got our dinitride pentoxide, water, and then nitric acid. So if I take a quick peek at my third equation, this dinitride pentoxide is unique. It is the product in our target equation. So this is where I am going to start. And I'm going to have to do something right away that we haven't had to do yet. I'm going to have to do two manipulations, actually, to this equation. The first one should be pretty obvious. In my target equation, I'm looking for 2 moles of dinitride pentoxide. So the first thing I'm going to have to do is multiply this by 2, which means that I am going to have to multiply my enthalpy change by 2 as well. However, you will also notice that this dinitride pentoxide is on the opposite side of the reaction arrow as our product. We have a reactant and we have a product. So if I were to add them together right now, they would cancel each other out, which is not what we want. That means that I'm going to have to reverse the sign of that reaction. I'm going to have to reverse that reaction. So I'm going to have 2 nitric acids decomposing to form 4 nitric acids, because I'll have to multiply by 2. 4 nitric acids decomposing to form 2 dinitride pentoxides and 2 waters. When I do that, and I will rewrite all of my equations so that they look nice and pretty and I can add them up more tidily, and that reaction looks good to me for now. So we're going to move on to our third reaction. We've got 1/2 nitrogen, 3/2 oxygen, 1/2 hydrogen to form nitric oxide. Well, I can see right away that I'm going to definitely have to change some coefficients. I'm going to have to multiply by 4 in this instance. My nitrogen is on the appropriate side of my equation. If I multiply this by 4, I'll get my 2 nitrogen. So I'm going to start off by multiplying that by 4. My nitrogen is on the correct side of the equation. My oxygen is also on the correct side of the equation. I know that I'm reversing reaction number 2, so my nitric acid will cancel out, which means that I only need to be concerned now, really, about my hydrogen, which means I need to look back up at reaction 1 again. When I go back up to reaction 1, so here I'm multiplying this by a factor of 4, which means I'm going to have 2 diatomic hydrogens. That means this diatomic hydrogen up here needs to also have a coefficient of 2. So I'm going to have to multiply my first equation by 2. You'll also notice right now that this hydrogen is on the same side, it's a reactant. And that means that I need to reverse this equation because I need to have this hydrogen as a product to cancel out this reactant hydrogen. That means, I've made a mistake already. Do you see what the first mistake I made is? Hopefully you noticed that I did not write my factor of 4 down here. That is incredibly important because if I do not multiply this enthalpy by a factor of 4, this enthalpy will not be proportionally correct and I will not get the correct answer. I almost missed my 4, but I'm not going to miss my sign change and multiplying by 2 up here. So when I do these multiplications across the board, this is what it should look like. I should have 2 hydrogens, I should have 1 oxygen, and then I should have 2 waters, 2 dinitride pentoxides, 2 waters, and then 4 nitric acids, and this reaction will be flipped. I will have 2 diatomic nitrogens. I will have 6 diatomic oxygens. I will have 2 hydrogens, and I will have 4 nitric oxides. So when all of that goes to plan, it should look a little bit something like this. Pardon, technology. All right, so here I've rewritten all of my equations correctly. I've flipped the signs when appropriate. I've multiplied by the appropriate coefficients. And I've lined up all of the reaction arrows so that everything will add up nicely. Now we need to do our addition. So I'm going to add my nice little addition symbols over here and over here as well. Going from the top down, I have 2 water as a reactant. I've got 2 water as a product. They will cancel one another out because they're on opposite sides of the reaction arrow. I have 2 hydrogen, and I have 2 hydrogen. Product, reactant, cancel one another out. I have 4 nitric acid, and I have 4 nitric acid, one as a product and one as a reactant. They cancel one another out. I'm going to leave that oxygen there for just a moment. We'll see what happens with that one in a second. Now, I have only 2 dinitride pentoxide, which should go straight down because that is our target. I have 2 diatomic nitrogen. I have 6 diatomic oxygen. However, I'm looking for 5, but this oxygen up here is on the product side. So I will cancel one of these reactant oxygens for a total of 5, which means we have the appropriate resulting equation. That means that we can add all of these together and we will come up with our appropriate enthalpy change of 28.4 kilojoules. I hope all of that was very clear. If it wasn't, or if you would like some help or support with anything, please feel free to send me an email. And best of luck with the practice problems for the week.